All right. So as Jiho said, my name is Colin. I'm kind of the other FlexFlow person here. And whereas Jiho works on a lot on the inference side of things, I work a lot more on the kind of compiler and training side of FlexFlow. So today I'll be kind of giving a high-level overview of that. I probably won't be going into as much detail as Jiho did on kind of any of the individual projects, but I'll be kind of trying to give just a broad overview of kind of what is FlexFlow, especially for those of you who haven't heard about it before besides Jiho's talk, and kind of what problems it's really trying to solve, and then a little bit of kind of looking at a bit of kind of the historical look back at kind of how FlexFlow started and kind of how it was architected then, and then how it has kind of changed over time and how this has kind of driven a lot of our decisions. So I guess to start off with, for those of you who do not pick up what FlexFlow does from the last half hour, FlexFlow does stuff for distributed DNNs, so distributed deep neural networks. And as I mentioned, the thing I'll be focusing on is training, which is kind of where FlexFlow started, though certainly over time we've kind of expanded over to inference as inference has become more and more important. And to better understand kind of the challenges of distributed DNN training and kind of why something like FlexFlow would be helpful, let's just kind of walk through a couple basic examples here of kind of doing distributed DNN training. So let's say I've got some simple model here like this. So I take in some input tensor. That might be, say, like a batch of images, some MNIST batch of images, or something like that. And I'm going to pass them through some matmuls. Each of those matmuls is going to have some weights that are going to be used and then backpropagated back across to update. So essentially, after every forward pass, I will proceed to update my weights. And then I'll compute some output tensor based on that. So pretty simple model. Obviously, things in reality are a lot more complex, but this will be sufficient for kind of our purposes. And we're going to imagine here that I actually have 2 GPUs. I'm very lucky. And I would like to train this model faster by exploiting my 2 GPUs. So a pretty simple thing that I can do, which probably all of you have heard of, is called data parallelism. In the DNN context, what this essentially means is I take my input tensor and I split it into 2 pieces, and I put half of it onto each device. And then I'm going to pass that into essentially the same matmul kernel, but a smaller one because it's only computing over half the data. Pass that again into the next matmul and compute the corresponding subsets of the output. So nice and simple. The only question I then have to decide is kind of how do I handle my weights, because obviously each of those matmuls now has a dependency on that weight tensor. And so in data parallelism, what I'm going to do is I'm just going to actually copy that weight tensor and put identical copies onto each device. So I'll put an identical copy of weight 1 and weight onto GPUs 1 and 2. And same thing for weight 2. But unlike inference, as I was saying in the beginning, essentially we're going to do a forward pass, and then we're going to do a backward pass. We're going to update our weights. And so if we simply sit here and keep running this computation back and forth on different pieces of the data, right, our weights will increasingly diverge from each other, and we won't train properly. And so what we're going to do by default is that after every forward and backward pass, we'll do an all-reduced operation to essentially accumulate all the gradients and apply them so that our weights stay synchronized the whole time. And so this is certainly one way of mapping this DNN onto these 2 devices. But as with most kind of high-dimensional linear algebraic things, there are a lot of other ones. And these other ones, these kind of other mappings, have rather complex kind of performance trade-offs that we're making here, right? So for here, what we've done is, well, we've at least gotten the ability to kind of saturate more of our GPUs. But this has come at the cost of we're kind of just using a lot more memory in total, maybe not more memory per device, but we now have 2 copies of weight 1 sitting around when we really only needed 1. Same with weight 2. Our kernels have gotten a lot smaller. So if we weren't saturating the GPU before, we're definitely not saturating it now. That can potentially be bad. And in the backward pass, we now have this rather expensive communication operation that we need to do in order to keep all of our weights up to date. So I got some wins and I got some losses. And it turns out that if I kind of look at any of these strategies, so let's, for example, imagine instead splitting it along this other dimension, that I would get a different set of trade-offs. So here, what I can actually do is I can kind of do a more complex form of reduction parallelism, where if I split in the other dimension, it turns out that, trust me on this, your matrix multiplication kind of data dependencies work out such that you don't actually need to duplicate all of the weights across each device for weight 1. And so I'm able to put half the weights on weight 1 and half the input and still compute a full-sized output there. But it turns out that I do then need to put let's say, duplicate them for weight 2. And then essentially what I will do actually is I will have computed essentially a kind of sum of the output. And so I'll need to take the outputs of each of these devices and sum them together at the end to get the kind of correct result. Advantage of this, I no longer need to synchronize weight 1. That's, compared to our last strategy, it's a win. But I'm still duplicating weight 2. Essentially this kind of summation property tend to be pretty focused on a single model class, maybe LLMs or things like that, because if you actually want to kind of get a lot of performance out of a broad range of models, it's actually quite difficult because of all of these kind of model-specific optimizations you end up having to make. So let's take that even further and let's consider, okay, well, let me actually exploit linearity here. I can kind of rewrite this operation, right, through using associativity to that, I think. And now this is kind of an equivalent computation. But kind of one thing that has shown up a lot in recent years has been kind of the existence of fine-tuning, where we have some model that's at least partially trained and we want to only update some of its weights. And so here, if either of these weights is kind of being trained, the fire icon is usually used to denote that we're training the weights. Well, then I'm going to have to kind of rerun this at every single iteration because I'll have updated my weights with the backward pass, and so I need to rerun the forward pass. Fine. But in the case that they're both frozen, then I can actually essentially pre-compute this whole thing and not actually run that piece and update, if this model was larger, kind of my other weights. And so here's kind of another lever that I have to deal with. If you want to be doing fine-tuning of various different structures, then whatever my kind of system is for doing distributed DNN training needs to be able to kind of take advantage of any of those little kind of ephemeral advantages that I can take, such as, oh, I don't actually need to update these weights. All right. And now if we go back to this, as I was kind of mentioning, most things are not actually linear in practice. A more realistic form of this model would have some values in the middle there. And we can look at kind of similar to that previous operation, kind of how can I modify how I do the operation? How can I reorder the way in which I do operators or change how my kernels function or something like that? And here the obvious one is, well, if I do this naively, I'm going to load all of my activations from the input tensor. I'm going to compute that matmul. I'm going to write them all back again. Then I'm going to load them all again, just do a very simple ROLU operation, and write them all back again. And that's kind of very unnecessarily wasteful of memory bandwidth. And so your kind of standard system is going to go, hey, look, I can actually kind of do a fused kernel here. And I can do the matmul and the ReLU at the same time and save myself a whole bunch of memory bandwidth. But if you notice now, that matmul plus ReLU is no longer linear, and so I can't use reduction parallelism. And same with this other one. But if you notice, based on the strategy that we used below, we actually only were exploiting linearity, it turns out, for the first operator. The second operator, you actually don't need linearity here. Essentially, kind of, you have to be very careful in how you make these decisions because a lot of things kind of interact. So don't worry if you haven't kind of understood all of the examples like super clearly. The main thing here is just to realize kind of how many different interacting pieces you have to deal with here if you actually want to extract maximum performance in these cases. So, essentially to kind of start to kind of take a bunch of examples and start to kind of formalize them a bit. If we want to kind of understand what our optimal training strategy is going to be, so kind of what the answer FlexFlow at least needs to give us is, well, one thing it's going to include is algebraic transformations, and this is just a fancy name for essentially all of those kind of rewriting or reordering operations I was doing, right? So when I exploited associativity of matrix multiplication, that would fall under an algebraic transformation. Essentially anything that is exploiting mathematical properties that operate. This could be also operator fusion would fall under this, kind of any of these kind of style of changes, which are normally expressed as kind of rewriting operations. So I have to consider essentially whatever FlexFlow is, it has to essentially identify the optimal sequence of algebraic transformations for my model. But it also has to identify the optimal parallelization. And as I hinted at, there's a whole bunch of different forms of parallelization. Even within parallelization, I also have to decide on my data distribution of all my tensors. And that's not just my activation tensors, but also my weight tensors, and also all of my optimizer buffers. And so I've got a whole bunch of different pieces that are interacting. And if I want maximum performance, I have to actually reason about those. And I can't just kind of overly simplify it too much. And that's bad enough, but the fact is I don't just want to do kind of one of these, either algebraic transformations or parallelization. I probably want to do both. As we saw, they can interact in non-trivial ways, right? If I fuse two operations together to make something nonlinear, that affects my parallelization opportunities. And so I actually need to be considering all parallelization strategies, all sequences of algebraic transformations, and kind of all products of those two sets. So we're starting to get very, very unscalable very fast. And this is bad enough for machines, but if you're doing this by hand, it is extremely hard unless you're kind of very specific to a model, because the search space just gets very large very quickly. But these, it turns out, are not actually the only things we need to do. If you actually want to be kind of running things optimally today, another thing you really care about is memory. And so we might need additional optimizations like activation memory materialization. And now we've got kind of 2 to the number of activation tensors I've got in my model. Sure, I could prune some down, but either way, another big search space. Oh, and again, we're considering the product of all of these things. So we're just kind of increasingly blowing up our space of solutions over and over again. And then I might also want tensor offloading. And tensor offloading and activation rematerialization can interact. And so suddenly I now have this massive space of all of these optimizations that are all interacting all at once. But okay, let's say I sit down and I actually manage to kind of figure out for my model what the optimal strategy is. Like I've been convinced by Jihao's talk, LLMs are the future. I sit down, LLMs are nice and simple, and I'm able to at least figure out, okay, this is kind of the optimal training strategy for an LLM. But the problem is, that's actually not the extent of the problem. I'm not only constrained by kind of what my model looks like, but I'm also constrained by what optimizer I'm using. Different optimizers have different memory usages and different performance aspects. Whether, again, kind of which weights I've frozen, which ones I am tuning. That's also going to affect and directly influence my solution. Quantization, if I've decided to quantize something versus not, that's going to change. If my values are smaller, then it's probably a lot easier to transfer them over the network, a lot cheaper. So that impacts my communication costs, might change all of my parallelization strategies. My batch size changes things. Network topology, so it's not just kind of model design things, but also exactly what hardware I'm running on, which a lot of people are running on very different hardware, and hardware keeps changing. And so if I actually want to be performant, I have to be kind of taking into account what your network topology is, what all the bandwidths are, how many GPUs are in your cluster, or the fact is you probably don't have exclusive access to your cluster, so whatever number of GPUs you have actually been allocated for whatever job that is, which may not be the number of GPUs you're allocated for next week's job. And so I have to have all of that flexibility. What is kind of the available amount of memory? What is the bandwidth between your CPU memory and your GPU memory? And kind of all of these are going to be impacting all of these different solutions. So now I have a real problem because I'm kind of dependent on, and this is a small subset of a huge number of different things. And even that just gives me like a kind of one ludicrously large search space that I still have to search over somehow. So this is kind of the problem that we're faced with. And so ultimately kind of jumping from, or taking kind of this machine model and model configuration as input and going to an optimal strategy, which is kind of the combination of all of those kind of optimal strategy aspects I talked about is what FlexFlow kind of does, at least on the training side. So Now I want to kind of just jump back and give kind of a bit of an architectural overview, talk about some of the kind of projects that either we've done or are ongoing. And again, this is kind of meant to be an overview, so if you guys have more detailed questions on any of these, definitely find me after, and I'm happy to kind of go through in any detail. I couldn't pick a favorite, so I decided to do all of them in 2-inch depth here. All right, so FlexFlow, as probably Jihao could tell me better, or tell you guys better than I can, started back before I was a PhD student in 2018, back in the early days when Jihao wrote FlexFlow and Tasso. So we'll kind of segment that off as one initial period. And then we've kind of got the current kind of timeline of FlexFlow, which has kind of been the last 3 years or so, where we've been pushing a lot of the compiler aspects as well as adding inference. And then kind of looking forward, kind of what we're doing from here. So we'll start off in chronological order back in 2018. And so one thing to note is that both FlexFlow and Tasso kind of are considering single optimizations. So FlexFlow is just considering, this is kind of the original FlexFlow paper, not the overall FlexFlow code base. Unfortunate naming collision there, but I've designated a /SOAP to denote the exact search space that searches over. But both of these are searching over individual search spaces. So Tasso is searching over algebraic transformations, and FlexFlow is searching over parallelization. And so some of this horrible exponential blowup that we have to solve in the kind of search or compiler end hasn't quite hit us as badly yet. And so this is kind of overall what the FlexFlow system looks like, minus the AMD backend, which I accidentally put in the wrong figure. Sorry, that should be in 2021 to 2024. Pretend AMD is not there. But so the user is going to pass in this kind of green graph on the left there, which is going to denote essentially the computation graph for the data dependencies of the user's model, along with all the other optimizer information and everything that I mentioned. And for the most part, we're kind of going to run a very small piece of a compiler on it because the optimization problem is not yet that hard. So the original version of FlexFlow, the kind of sizes here are somewhat representative of kind of how this looked. The actual kind of compiler logic that was involved was relatively small. And a lot of the logic instead was just kind of taking this ML computation that is produced, this distributed computation, and executing it on your giant machine. And so that's kind of where Legion comes in. FlexFlow kind of from the beginning used Legion as its kind of underlying kind of layer for doing distribution. FlexFlow actually is just essentially like a Legion application, like any other, just with a kind of weirdly large and expressive input. And so that's ultimately kind of where the bulk of the code was, kind of from 2018 to 2021, roughly. But moving forward to kind of 2020, 2021, the big change was kind of Unity, which attempted to, as opposed to doing each of these optimizations independently, to actually try to do them jointly. So Unity attempted to do both algebraic transformations, essentially the Tasso piece, and parallelization, the FlexFlow piece, all together. And not sequentially, not kind of considering one and then considering the other and combining the solutions, but actually just considering this all as one exponentially enormous space. And there's a whole bunch of kind of machinery necessary to make that work because obviously combining exponentially large spaces, at least naively, tends to blow up in your face rather badly. But just to give you kind of a hint of kind of, I think, one of the key contributions that came out of Unity is that we realized essentially that we could exploit the structure of a lot of these actual computation graphs and the actual data dependencies involved. Because it turns out that ML computation graphs are not arbitrary task graphs. They actually have some structure almost all the time. And so it turns out that there is a kind of mathematical construct called series parallel graphs that were discovered in the late 1800s and then actually worked on by Tarjan and some of his students here back in the 70s. That kind of turn out to very accurately express most of the patterns that we see in DNNs. And also the kind of advantage of being much more analytically kind of tractable for doing optimization over. So as a quick definition, series parallel graphs are inductively defined. So we've got a base case of a single graph node. We can do the parallel composition of two graphs, which just consists of putting each of the graphs next to each other with no additional edges. Or we can do the series composition of two things, where we put one and then we put the other, and then we essentially put kind of a data dependency to enforce ordering here. So in order to make sure that everything on the left runs before everything on the right, we put in essentially an all-to-all kind of edge connection here. Now this is kind of constructing the set of series parallel graphs, but obviously what actually happens for FlexFlow is we get handed some giant computation graph and get asked, what is the series parallel decomposition of this? So just to kind of walk through one small example, let's say our computation graph looked something like this. This is a little more densely connected than most of them look in practice, but it's a kind of good adversarial case. We can identify that at the top level, this is actually a kind of series split across that layer there. Because how can we tell? Well, essentially, if we look at the actual data dependencies, it turns out that kind of everything above that line has to execute before everything below that line. And that gives us a lot of information, right? Now we don't actually have to worry about kind of optimizing the whole graph, because we know that whatever kind of the cost is going to be, it's going to be the cost of the first thing plus the cost of the second thing. They can't possibly run at the same time. And so my job becomes essentially as simple as just make the first half of the graph run as fast as possible, make the second half of the graph run as fast as possible. And by doing that, I've made the whole graph run as fast as possible. And then I can essentially just do this recursively. So I can identify parallel splits, more series splits, kind of go all the way down to the individual node level. And now I've kind of found a way to analyze or kind of optimize this graph much more attractively, because I'm able to use kind of divide and conquer means over this graph. So as opposed to having to do this, consider the entire computation graph and all of the global performance aspects of it, I'm able to consider much more local subproblems and then just kind of have principled ways to combine them. And it turns out this is kind of not just some coincidence. It turns out that actually there's kind of quite a few kind of fundamental graph problems that you probably learned about in some algorithms class at some point or some complexity theory class that are actually kind of provably more efficient over series parallel graphs. So they provide kind of a very convenient construct. Now the way that most kind of things handle these more complex topologies nowadays is they do an even kind of stronger restriction, which is they make everything a straight line. And the problem, that also gives you great analytical properties in terms of optimizability, because straight lines are really nice, just sequential splits all the way down. But the problem with that is you really start to incur non-trivial approximation cost. If I have a graph that is very wide and not very deep, then suddenly I'm kind of losing a whole bunch of potential parallelization opportunities by putting everything in a line. And one advantage of series parallel graphs as opposed to that is it turns out that in fact, for pretty much all graphs, or pretty much all DAGs, essentially there's a series parallel graph that is very close by, and that essentially you can get to a series parallel graph by adding just a couple extra data dependencies that essentially have very trivial data dependence cost on the order of a few percent maybe at worst. So it provides a kind of very convenient intermediate that gives us both analyzability as well as kind of being flexible enough to handle whatever users want to throw at us. All right, so that's Unity. And as you can tell, we kind of went from some very simple compiler stuff to suddenly having kind of this large theoretical framework over which we need to optimize things over this very large space. So the kind of amount of kind of machinery in our compiler is definitely getting a lot larger. GraphPipe is going to take this even further. So this is a recent paper that I believe was just accepted, I think. Yes, I believe ASPLOS, yes. But essentially what GraphPipe does is it kind of builds on Unity, uses the kind of series parallel decomposition kind of abstraction, but brings it essentially to another problem that people run into, which is pipeline parallelism. For most models that are straight lines, pipeline parallelism is pretty simple. You just kind of pipeline your operations through, and as long as you have a sequential dependency of stages, that's kind of a pretty obvious kind of operation. You don't really have a whole lot of kind of choices involved. Not saying it's easy, but you can definitely get a lot worse as soon as you start to actually have branching models. So what GraphPipe does is essentially it takes models that might have branches, or that have a branching structure, and is able to actually find parallelization schemes for these. And so especially for models that are not just a straight line, you can suddenly get large performance improvements on things like recommendation models are a common class, multimodal models that might have kind of interactions between different modalities. It turns out that in a lot of these cases, having more expressive pipeline parallelism is very useful. But of course, this also just adds kind of more and more load and more complexity into FlexFlow's compiler. And then inference also happened in this time period, but you already heard from that from Zhihao, so we'll skip that. But looking at these two, and I'm almost done, so I will not go that much over time. as we've seen, both Unity and GraphPipe are pretty heavily substantially on the kind of optimizer aspect. They're not substantially increasing the complexity of the runtime in all ways, but they're definitely increasing the complexity of kind of the decision-making logic in FlexFlow's compiler. So kind of over this time period, we've seen a rather large increase in the kind of amount of code and the amount of complexity that is happening in FlexFlow's compiler as the number of optimizations that we've had to consider has increased. And this has kind of increasingly become an issue because, as mentioned earlier, FlexFlow was not really originally architected to have a kind of large and complex compiler piece. And so one thing that has happened over the last few kind of 2 years is we've been really working on essentially kind of making the compiler and the optimizer kind of a first-class citizen in FlexFlow and attempting to kind of reorient things so that the kind of code base is more maintainable with that kind of future direction in mind, since that seems to be likely that we will kind of essentially need to keep adding more and more optimizations as essentially the demands for ML performance get even more stringent. So, as kind of more of a practical engineering thing over the last year, we have gone from, well, I mean, effectively 0% code coverage because we weren't tracking it, to about 80% now. So there's still a ways to go, but I'll take 80% over 0%. And so, things like that in terms of maintainability have gotten a lot better. And this is not only nice for my sanity, but also opens up a lot of new opportunities. So kind of looking forward for the next few years, one key thing is to kind of understand what the new structure of kind of FlexFlow's code looks like. And the key thing here is that really we have a lot more pieces that are pulled out, and a lot more of them are kind of runnable in isolation. So I know there's been, I believe we got a question at some point about kind of using FlexFlow's compiler outside of FlexFlow. So, I don't remember if it was interest from the Leagate team or someone, but potentially kind of being able to experiment around with that. In the old architecture of FlexFlow, I mean, in principle you could. In practice, good luck. But essentially with the rewrite, this now becomes possible. We can also take kind of the core data structures that are functioning. The PCG is kind of the core intermediate representation over which Unity functions. And we're able to export that to JSON files. So we're now able to kind of jump around between different runtimes. So as Jihao mentioned, one thing that we were looking into is kind of dropping down and instead of using Legion, which is in some ways almost way too powerful for our actual demands on the kind of underlying distributed system. We could try to instead use Realm directly. And whereas this would have been a disaster in the old FlexFlow, this actually becomes quite trivial when you've kind of pulled out and nicely segmented all these pieces. And it's just a matter of kind of taking that JSON file and dumping it into a different runtime. And so overall, things are a lot more modular, which is good because we're kind of looking at adding a whole bunch of new optimizations here. And the key category here, which we've been working on for a while, is memory optimizations. Very important for a lot of kind of very large models. A lot of the complexity here really just comes in, well, both on actually getting the Legion implementations is a bit non-trivial. Combining some of these with tracing is not always the smoothest operation because essentially tracing does not like to free things, whereas obviously some of this requires freeing things pretty aggressively, and so you end up having to re-implement some of the memory management stuff in FlexFlow itself. But then there's also a lot of kind of search time complexity as well due to kind of all of the various kind of increased forms of asynchronicity of a lot of these optimizations where you might be moving data around between different memory, but also recomputing it, and so like really trying to saturate the machine, you have a whole bunch of different things running at a time that becomes hard to analyze. Another project that is ongoing on the compiler side is if you look at kind of what is increasingly becoming the bottleneck in Unity and a lot of these systems, the problem is you end up, in order to have these operations kind of coexist, having to drop down to kind of the lowest semantic layer, which tends to be kind of a rewriting system. And while rewriting systems are very expressive, they're also a huge pain to optimize because it's very hard to kind of think about, okay, what happens 19 rewrites out from my current position? And so one technique for improving this that at least some of you have probably heard of is eGraphs. And so Septal is work with another of Alex's students, Rupanshu, who was at least here yesterday, on essentially trying to see if we can take Unity and to essentially port it over to use eGraphs, which has a lot of non-trivial challenges due to the need to maintain series parallel structure. But kind of the old goal there is that if we're able to do that, then that kind of provides a bit of a solution where we can start to put more optimizations in without kind of really having to worry nearly as much about scalability. And then the final project, just to touch on, is I mentioned that a lot of models were series parallel. I did not mention that all models were series parallel. And that's because, in fact, not all models are series parallel. The vast majority are, but not all are. But as I also mentioned, essentially the approximation cost for those models that are not is actually quite small. And so one project that we're working on as well is looking at kind of how to better approximate non-series parallel graphs as series parallel. And this actually comes in handy not only for essentially the actual or kind of increased broader model support, but actually ends up having a lot of internal ramifications for how FlexFlow does search at all. Essentially, it turns out to be possible to phrase a whole bunch of FlexFlow searches as simply approximating non-series parallel task graphs to series parallel task graphs. And so that's actually kind of a direction we're really excited to pursue as a way of kind of potentially increasing scalability to more optimizations. So with that, that's Pietro there in the back if you're interested in talking with him. That's everything. Obviously, I know I kind of jumped through a bunch of things at a very high level, but if you're interested in kind of any of these directions, let me know, and I'm happy to go into excessive amounts of detail offline.